No, the original is not like that. This is the 1985 digitized version.
Well, we'll treat it as a special event, not a bug.
Yeah, so 640 by 480.
Oh, okay.
You get it to high resolution.
Yeah.
You're experiencing technical difficulties. You get it to?
Oh, too dark. So it's too dark.
Yeah, the
Yeah.
resolution is off. Yeah, that would be good. I'll just open and log into Gmail again. Okay, so anyway, we'll talk about credit risk. I got a board over here. We don't even have sticker slides.
You can go through this in the first 2 minutes. You can go through with this. I will just say.
Okay. Oh, now you're on the other screen now. Okay, anyway. So, what are we concerned with? Credit risk modeling. There's basically two approaches, historically speaking. You have the reduced form models and the structural models. All right, the reduced form model, you have some stopping time, tau, which you usually don't talk about. What you really talk about is the probability of surviving to time t being e to the minus integral of lambda dt. So lambda then is the hazard rate, and s is representing the survival curve. Okay, so basically, this curve is what you would get if the time that the default occurs is exponentially distributed, like a Poisson process, jump to default. The other models.
But wait, I mean, you can just say that the lambda there is defined by this equation,
Yes.
and forget about models. It's just
Right.
a definition.
Yeah, this is just, we'll get to that exactly.
Okay.
Okay. Right. So, right, that's the classical reduced form model. Exponentially distributed arrival time, unpredictable default time. We'll get to what that means, totally inaccessible. And we have references, which I can barely read. In any case, then we have our classical structural models. Structural models, we usually have a continuous process X, which is evolving over time. Think about it like the assets of a firm. You have a barrier we think of as the debt that the firm owes, and when the assets hit the barrier, you get your default. And then we talk about how do you model the assets process, how do you calculate the debt level, and things of this sort. The default time is a consequence of this process hitting the barrier. Okay, so this is the classic thing is the Merton model, where the barrier is just a level at one particular time, capital T, when the debt has to be paid. And either you default if you're under the barrier at that time, or you don't default if you're above. Okay, extended to the Black-Cox model, where you have a barrier over time, as well as a terminal level that you have to be under. That looks a little better.
Yeah.
Okay.
It's actually okay.
Yeah. Okay, so leave it as, okay.
Okay, so that's the classical structural models, right? Now we have the notion of the contemporary default model, right, which is a little different. Because originally the notion of a structural model was that you were modeling the structure of a firm. Reduced form models, you're kind of ignoring the structure, you're just modeling the default time itself. However, if you look at the literature over time, you'll see that more recently, any model where you're modeling the default time that is called a reduced form model, even if the model involves modeling the assets and the liabilities, which you would think of as being structural. And conversely, any model where default occurs when a process hits a barrier is called a structural model now, even if it has nothing to do with actually trying to estimate assets and liabilities. Okay, now there's some literature where, and that's what I just described here. Okay. Now, if so, one way that people started looking at this is that in the reduced form models, there's never any information to know that default is about to occur. Okay, the default is totally inaccessible. Whereas in structural models, you have a continuous process hitting a barrier, you have information about the default is about to occur because you get close to the barrier. The closer you get to the barrier, the more likely you're about to see a default. Probability of hitting the barrier goes to 1 as you approach it. And the default time is predictable. And these are seen as kind of two ends of a continuum, from totally inaccessible to predictable.
Right.
And the models kind of lie on this spectrum. But there's no formal way of expressing all these models. One approach to it is from an informational point of view, right? Like Setzin, Jarrow, Prater, and Yildirim, Geske rather, Jarrow and Prater. The idea being that, well, if you have this barrier model, for example, you have a continuous processing barrier, but you don't have all the information. Like, for example, maybe you know the value of the process at time 0, but you don't know it in the future. Or you know the process in the future, but you don't know exactly the barrier. You have uncertainty about the level of the barrier. In that case, then you're injecting uncertainty into the system, and you're getting a lack of predictability. So their whole approach is to kind of fiddle with or remove information, remove appropriate information, and try to use the filtration to express what you know about the system, as opposed to using the filtration to express kind of the state of the world at a given time with all the information. Okay, so, but we don't really have tools for playing with filtrations. You can't easily just modify filtrations. So it's not, I mean, while it kind of tries to unify everything, it tends to be, well, the models don't end up being on a uniform framework because we don't have the tools for it. So all the approaches tend to be ad hoc, like taking a continuous model where the default is predictable and injecting a lack of predictability by throwing away some of the information.
I guess you'd really like a model with a dial. The one extreme gives you
Exactly.
or structural, and the other extreme gives you, exponential.
So that's what we're going to try to do. Okay.
But what if it's a Markov process? Then wouldn't that be that sort of conditionally give you more information and the filtration?
Well, if you have a Markov process and the filtration is generated by the process,
Yeah.
then you'd have, and the process is continuous, then you'd have a predictable model.
Correct.
If the process has jumps, you'd have a certain amount of non-predictability. So the way I'm going to approach this is that there are 3 different pieces you have to worry about, right? There's modeling of the default time itself. There's what happens at the default, right? What are you recovering when default occurs? Because you presumably want to value something. You need to know what you're getting if there's no default, what you're getting if there is default. And that's a whole separate branch. And then there's the valuation model. Now that you know what you're getting under all situations, you can try to figure out what the value of the whole package is. So you need to understand each component, you need to model them. You shouldn't start just jumping into valuation until you've pinned down the first two. So we're going to focus on the first one, just the default model. And the idea is going to be that all default models can be expressed in terms of this sort of reduced form framework. Not with a survival curve, but with a bunch of survival curve processes. And what this does is it gives you the same mathematical framework for expressing all these models, and then you can start comparing them, combining them, and doing things of this sort, analyzing them. And moreover, how much predictability you have, it appears that you can read directly off of these processes, rather than having to work with the abstract notions of accessibility and predictability. So some references, Chan and Kenyon Green. And the reason Dirac process, you'll see why Dirac processes show up. Okay, so let's start with the survival curve process. Let's nail down our settings. And let me turn off my phone. Noise. Got two phones.
Yeah.
Separate campaign phones.
Uber calls, you're not going to answer.
So secure. Yeah, no, Mike, sorry, I'm busy. Okay, so we have filter probability space, standard setting, you have your sample space, your sigma algebra, real world probability measure, and filtration. And we're not going to even worry about risk neutral because we're not doing valuation. We just want to pin down exactly what's happening under what conditions. To some extent, we don't even really need the probability. So, all default models you can think of as expressing a stopping time, time at which the default occurs. Random variable respects the filtration, so it's a stopping time. Okay. Whereas usually you'll see in reduced form models, they kind of leave the filtration out because it's totally inaccessible anyway. We're going to just keep it in the filtration. This is the usual map you see in classical reduced form models. You have your stopping time, your survival probability, the probability density function for the stopping time, and the hazard rate. And survival is given by the probability that you haven't stopped yet, you haven't defaulted yet, which is the expected value of the indicator being greater than that given time, which is also 1 minus the cumulative distribution function. And then the probability density is the negative of the derivative of the survival, because it's the derivative of the CDF. Which we can just integrate out, of course, to get the survival. We express the survival curve. So the survival curve is starting at 1 because you haven't defaulted yet, and it's dropping over time. And it goes to, maybe it goes to 0, but it doesn't go negative, so we can express it as e to the minus integral of a function. Lambda then, that function is the hazard rate, where if everything is smooth, you can express as the density divided by the survival curve, but in general it's really the negative of the derivative of the log of the survival curve, which we'll run into issues with, but we will explain how to handle them to some extent. Okay, so that's classical reduced form math. So to extend this to stopping times in general, if you think about it, all of this is just expressing what tau is doing in the future given today's state. But as time evolves, we want to know what is going to happen, what all this information looks like in the future, right? Depending on what's happened in the past, the firm might be more likely to default, less likely to default, right? The stopping time might come sooner, might come later. So in general, you can't just look at the survival curve or the hazard rate curve to express the stopping time in general, you have to look at them in the future as well. So how do you do that? Conditional expectation. So we'll define the survival curve process to be the conditional expectation at time little t of the indicator that tau is greater than big T. So it's essentially the probability at time little t of surviving past capital T given the state of the world at time little t.
So are we thinking of capital T as a variable or a constant?
Variable.
Okay.
So for every t, for every cap t, we have a process.
Okay.
Okay, and then we're going to derive the relationships between these different processes.
Okay.
And similarly, the hazard curve process. For every little t, for every cap t, we have a hazard rate process, lambdas of little t.
Okay.
Okay, and we integrate over the cap t to get the survival curve. Okay, and we're going to see that all default models can be expressed in this framework because we're going to get a bijection between family of survival curve processes with certain properties and an arbitrary stopping time. Okay, now one technical complication is we're defining the survival curve process by conditional expectation. You'd think this would give you a process, but it doesn't exactly give you a process, right? Because it gives you a process up to indistinguishability, meaning that the t expectation of this random variable is anything which gives you the right integrals that's known up to measure zero sets. Or in other words, you can change it on any measure zero set and you still have a realization of the conditional expectation. And now we want a process out of this, which means that these measure zero sets could be different every time little t, which complicates things, which makes it like an uncountable number of different processes that are all varying at different times and don't really have exactly values at these times. We want the values. Okay, so one thing we can do is try to select a particular version that works.
Can you just remind me what that expectation ET?
That's the conditional expectation of this random variable conditioned on the filtration of time t. So, first of all, we're going to take S sub cap t of cap t to be exactly the indicator. And then we're going to take the right continuous with left limit version of this process that matches these conditional expectations. That at least pins it down. That always exists. It's unique up to, like I said, up to indistinguishability, up to one measure zero set essentially for each time cap t. So that's about as far as we can pin it down for now. For some of the results, we need to pin it down further. We'll discuss the complications that show up. So we're taking the RCLL version for each time cap t of this process. Okay. Now, similarly, once we pin down one of these realizations, we want to define the hazard rate process to satisfy this equation. We should be able to integrate it out and exponentiate and get the survival curve. However, survival curves can have jumps. If you think about the Merton case, the probability of defaulting is 0 until this time when it jumps to the probability of being below that barrier.
Yeah, so you're talking about discontinuities at cap t as opposed to discontinuities at little t, right?
Yes.
Okay. Yeah.
Right.
Okay.
Okay, so on cap t it can have jumps. You might even want jumps in little t, I guess.
Okay.
Let's think about it. But in any case, since you're integrating it over up to cap t and it has jumps in cap t, it means that lambda actually has to have Dirac deltas in it.
Good.
So it's like this Dirac delta process.
So at the termination time, there is definitely a jump in cap T, correct? Because it goes from 2 to...
Yeah, you can say, if you were to consider little t past cap t.
Yeah, we usually only take little t up to and even to cap t. Right, prior to a default, there's a probability of defaulting. At the default, STT, well, we'll see what the values are, we'll get to that. Okay, so we're going to say that lambda is just the distributional derivative of the negative log of S. Okay, so essentially think of it as this we don't really know the process, but we know it's integral, essentially, per se. Now in Chen, he takes lambda to be that ratio, and like I said, that doesn't work where if you have jumps, and you often have jumps in the case where in a continuous process, actually, so this ends up not being a particularly continuous process either, but this one does. Okay, so now what I want to do is point out that what we're doing here for modeling stopping times makes everything look exactly like the HGM model. Okay?
Except for, like, forward rates nowadays are thought of as possibly negative, but lambdas can never be.
Okay.
Yeah.
Right. So if we think about the price process, right? Like a zero coupon bond price process, time at time little t, getting $1 at time cap t. And we have f sub little t of cap t, the forward rate for cap t observed at little t. Right? We have the price process is between 0 and 1, barring negative rates. And the credit, the survival probability is between 0 and 1. Okay? The prices are monotonically decreasing in t, in cap t, just like the survival curves are. The survival curve effectively looks like a discount curve. The zero coupon bond price is e to the minus integral of the forward rate, just like S is e to the minus integral of the hazard rate. The key big difference is that ZTT is 1, whereas STT is 1 or 0, depending on whether or not you've defaulted. And the other big difference is usually we think of the price processes as being smooth, whereas for the survival curves, they can be discontinuous in cap T. Okay. But otherwise, kind of the math looks very similar. Looks about the same. Now let's talk about the properties of these survival processes. So, if you have a stopping time, you're stopping at time cap t in some state, that's basically happens if and only if that's the first time that the survival probability becomes 0. Similarly, the set of states at which you've already stopped is the set of states by time little t is the set of states where s little t of little t is 0. And similarly, the states where you haven't stopped are the ones where s little t of little t is 1.
What's the first condition?
You're stopping at time cap t if and only if cap t is the minimum, is the first time basically that s becomes 0. Okay. So moreover, we have these other properties. We have that s sub little t of cap t is monotonically decreasing as function of cap t is right continuous with left limits. We picked it that way. It's between 0 and 1. For each little t in cap t, it's a bounded variation function on bounded intervals. So it's just bounded, period. So it's a bounded variation. It's about monotonic and bounded. That's all you really need here. And then it's equal to the conditional expectation of the future process as well. So, or in particular, for each cap t, it's a martingale. And of course, we already mentioned this about the CDF, conditional CDF in general. We talked about the
Just to be clear, it's a P martingale, right?
Yes.
Yeah.
Yes. In fact, they're all simultaneously P martingales, which is different from the HGM setting where you have to pick up numerator divide to get things to become martingales. Okay, now moreover, so given a stopping time, we can construct these hazard rate curve processes and they satisfy these 5 conditions. Now conversely, if we have a family of processes satisfying these 4 conditions, then there exists a stopping time for which these processes are actually the survival curves. The requirements are st of t is always 0 or 1, it's an indicator function. STT has to be the sup of st prime t prime for t prime greater than t. This has to start at 1, and they have to all be martingales. Okay, the conditional expectation condition is sufficient for it to be a martingale because it's bounded between 0 and 1.
Is there a typo? Like, I mean, on the last equation, st, yes, little t capital T is expectation of itself. So that doesn't sound right. So is it a typo, maybe?
That should be cap T.
Okay.
Yes.
Okay.
Thank you. Okay. So if you have these 4 conditions, you have there exists a stopping time tau for which the survival curves, these processes are the survival curves. And what's going on here? Really, the critical condition is the second one, right? Because basically, the idea. Well, I have the idea over here, right? Basically, if you think about it, you have these sets. The stopping time is essentially equivalent to these sets where tau is less than or equal to t. Okay? These are sets that are increasing. So there's this nested family of sets indexed by time. And if you know the stopping time, you get this nested family of sets, and vice versa. If you have a nested family of sets determines a stopping time by stopping at the first time a point enters into the set. Okay? So that's basically the whole argument. These are indicator functions. S of little t is an indicator function, so it's indicating the basically S little t of little t equals 0 is the set on which tau is less than or equal to t. That sup condition is the condition that makes them nest properly. So between those two, you immediately have a stopping time, which the indicator of tau greater than t is st of t. Of course, we have to start at 1 because we're starting undefaulted. And then the conditional, the fact that it's a martingale basically makes it the survival curve process. So we have this bijection between stopping times and families of processes with these properties. So we can define this default model by either specifying a stopping time or specifying this family of curves, family of processes. So you can go back and forth and work with either one. Now similarly, you can do the same thing with the hazard rates. All you have to do is translate those conditions on the survival curves into what it means about the corresponding hazard rates. So for example, STT being 0 or 1 means that lambda TT can never be a finite weight point mass. If it was a finite weight point mass, ST of T would be less than 1, between 0 and 1. Right, either it's an infinite point mass, which makes ST of T 0, or it's a finite value in which ST of T is 1. Okay, and then we just push through the same conditions. The annoying condition is the left. There's no clean way. Well, there is a clean way. We'll get to the way. But when you just put directly, right, these 4 conditions, the first 3 kind of directly translate to conditions on lambda. The 4th one, you just have to kind of replace S with e to the minus integral lambda until we do some more work.
The typo's there too, just so you.
That was the same, backed up, that's the same slide.
Oh, same slide. Okay.
Same
That's
slide,
why I
same
said-
typo. Okay. Oh yeah, there's a typo over there.
Okay.
I have to not go back past 21.
Okay.
Very important. Right there, I don't have the typo on this one.
Right.
That's the correct one.
So just one quick question.
Yeah.
The lambda that you refer to, in terms of practicality, what does that refer to? What is that?
It's like the arrival rate of default.
and that is updated regularly.
Well, it's whatever it is at any given time. So this fourth condition we have to do something about. Okay. But if you think about it, going back to HJM, right, if you trying to write down the conditions for the lambdas to be hazard rate processes is like writing down the conditions for forward rate processes to be true forward rate processes, right? You have a drift condition. So we'll go and derive that. Let's say our survival curves are actually continuous processes. We don't have to have any drift because we know they're all martingales. And we know they're positive or non-zero, pretty much non-negative, so we can write them as ds is s sigma dw. So then we can say, okay, given the fact that s has to look like this, what does lambda have to look like? So, well, if lambda has some drift and has some volatility, we see the volatility has to be the negative derivative of the volatility for the survival curves, and the drift has to be the integral of the volatility times the volatility, which is...
Just like a comment.
Yep.
So the little s's live in the interval 0 to 1, right?
Yes.
Okay, so you can do this, there's nothing wrong with this, but I'm thinking it's not the most natural choice of where to start. Because if sigma were constant, for example,
Then it wouldn't.
Yeah, exactly.
Yeah,
So-
sigma's not going to be, that's why it's a sigma process.
Right, so
Yeah.
I'm not against what you're doing, but I'm saying maybe a better way to proceed, okay, is to sort of build in, I'm thinking kind of like logistic type dynamics instead of geometric.
Right, so you can express S in terms of a logistic function of like another process, for example.
Yeah,
Right.
and then a
Sure.
logistic formulation, you could set the equivalent sigma there to a constant and
Yes.
define. Right.
Mm-hmm. But then you would still have the integral of that function's behavior over kind of where the lambda is going over time would be driving the sigma over here. And you would, you differentiate, might be interesting, yeah.
Yeah, I mean, like, let's say, you could make this even simpler that you have and just do ds is something dw, but then let's say, now it's something, it's got a lot of conditions to keep s both above 0 and below 1.
Mhm.
So, so let's say
Sure.
I'm trying to,
Yeah, that'd be interesting.
okay.
So in any case, but given this, putting it into this form with this sigma, then what has to happen for the survival curve, for the hazard rate processes rather, is exactly what you would expect, the same HJM condition. Because they're all martingales. That's exactly where the HJM condition comes from. The only difference being you would have, what would you have different? Well, you'd have a drift here, and you'd be dividing by a numerator and getting rid of the drift, and all that kind of stuff. You don't have that complication. Okay, but it gives an implication, right? If we have two hazard rate curve processes, then the sum is a hazard rate curve process only if the correlation is 0 or one of the sigmas is 0. Because otherwise, basically the vols aren't going to add up correctly. You won't satisfy the drift condition. Right? You add the two lambdas, and you'll have a certain drift, but the drift has to satisfy this. And unless the correlation is 0, the drift won't be right. Right, and basically the idea, basically what's going on behind the scenes is that if you're adding the two hazard rates, then the stopping time should be the min of the two corresponding stopping times. And for the min, and the min of the two stopping times will only have the hazard rate being the sum if the two are uncorrelated. Okay, so let's get on to predictability. Key difference between the reduced form and the structural models is predictability. So let's define that and look into it a little bit. So when we say that a stopping time is predictable if there's a sequence of stopping times that converge to it from below. this is called an announcing sequence. You know that, right, if tau of million is stopped, you're pretty sure you're getting close to a default. Accessible is if it's covered by predictable stopping times, basically, right? And formally speaking, you have a countable set of stopping times such that the probability that tau stops in a given state is equal to one of them is probability 1. Okay, so really the probability that you stop at all. Right, so you have to always worry about the states where you never stop. That's called a sequence which envelops lambda, a tau rather. And then you have totally inaccessible is if for every predictable stopping time, the probability that the given stopping time is equal to it is 0. So it has probability 0 of equaling any stopping time. Okay, so how do you think about this? Predictable is basically you can see the default coming. Right? You can predict it with increasing certainty as you approach a default. Accessible is kind of like you know the times at which a default occurs, but you don't know the states. Right? You know that the company has to make a payment in a year on this particular date. You don't know if they're going to make it or not. If they don't make it, they default. If they do make it, they don't. That would be like an accessible default time. Totally inaccessible is you don't know when they occur, you don't know which states they occur in, you only know the rate at which they occur. Okay, so, or in other words, predictable is like the default times and the states are known in some sense. Accessible, the times are known but not the states. And totally inaccessible, both the times and the states are unknown. So, for example, as we mentioned, continuous processing a barrier is accessible. You just put higher levels of the barrier, hit the higher levels. The times that you hit the higher levels converge to the time that you hit the barrier from below.
So can you kind of say that the Argentinian default situation is accessible, but not predictable?
It could be, yeah. It's just messed up. Accessible and not predictable would be, for example, you have particular times t sub I at which you're flipping a coin to see whether the default occurs or not. You don't know you know the times that it's occurring, but you don't know what's going to happen. Okay, accessible and not predictable is almost, if you think about it, is also almost like any gambling game. Accessible and not predictable is also, you take a continuous process that's hitting a barrier, but when it hits the barrier, you flip a coin to see if it defaults or not. That would also be accessible but not predictable. And then totally inaccessible is kind of like continuously flipping coins at the rate given by the hazard rate. So that's the intuition. Let's look at some real examples. As we mentioned, reduced form model, we have a hazard rate. Let's say it's a deterministic process. Our survival curve is equal to minus integral of the hazard rate. Given that we have a default, this is how we would usually write it. Right? In our framework, you have to throw in the indicator because you want this to be 0 at the times where you defaulted as well. So we have to write the survival process a little differently than you would ordinarily write it in a reduced form model. And what you can see, well, we know it's totally inaccessible. We mentioned that. Default can only occur at times where HT is positive. Right? If the hazard rate is 0, you can't have a default at all. And now, if you think about it, this is an important point, which you'll see why it's important as we go through these examples. But if you look at the survival probability, the probability of surviving past a certain time cap t, as you approach that time, the limit is always 1. in these models. Right? You're taking the limit of this process as little t approaches cap t, and it always goes to 1. So on the set that you haven't defaulted yet, right? If you've already defaulted, it obviously goes to 0. But in particular, at the times on tau greater or equal to cap t, right? Of course, the times greater than cap t, of course, it stays 1 because you haven't defaulted yet. At the times less than cap t, of course, it becomes 0 because you've already defaulted. But at cap t, it goes to 1, even though you're defaulting at time cap t potentially. Okay, Merton model, we have geometric Brownian motion for the firm value. We default if the value is less than some level at time cap t. We mentioned that before. We can write that down in a unified framework by just writing down the survival processes. Right? If you're less than or equal to cap t, the probability of defaulting is 1 if you're before cap t, and it's equal to the probability being below that level given where you are at time little t. At cap t and after that, you don't default, so your survival is the same probability. Right? So your survival curve is essentially doing this. Here's your cap t. Survival curve is always doing this. And the drop down here is the probability that wherever your process is, the probability it's below here. Okay? And then after cap t, it's just the indicator that whether or not you defaulted, of course. So you're never defaulting again. It becomes a constant.
Okay, so this expression 1 minus q norm times indicator, are you saying if t is strictly before capital T?
If t is less than or equal to cap t.
Yeah, I see that. Yeah. That's what you're writing. But now I'm taking the case when t is strictly before capital T.
Then it's well, there's a u also.
Okay, and u
Right,
is...
t is less than or equal to cap t, and u is greater or equal to little t.
Yeah, so let's do that.
And u is, right, so you have a time, right? U is, so you're, right, so you're,
Oh, I see what you're doing.
Yeah.
Okay, that's fine.
okay?
Okay, I got it now. So, so let's say
Yeah, so
we
you've got
consider
this,
a u
you've got
before...
this cap t,
yeah.
you're at this little t, and you're looking at, given where you are as a function of u, right? U is some time in here. And
Yeah,
if
then
u
the
is less than or
indicator
equal to cap t, you're
is
1.
off, like
then you-
0, so you get 1.
Yeah.
Right, okay, that's fine.
Okay. And now if you look at this, what's interesting is that the limit as you approach u of s of t of u is equal to su of u. Okay, always. If s becomes 0, this limit goes to 0. If s stays 1, the limit goes to 1. As distinct from this case where the limit's always 1. Then we can combine things. Let's add an accessibility to Merton. We'll take, we have those two survival processes, we're just going to multiply them. Multiplying the survival processes is adding the hazard rates. The stopping time becomes the min of the two.
Okay.
Now some defaults are predictable and some are totally inaccessible. And you get these funny limits, right? For the times when Merton stops before the reduced form model, the limit is equal to 1. Where did I say m prime? Oh, right, m prime. Right, m is the combined. M, right, m is the Merton, the reduced form, and then the prime is for this one, the Merton with the with essentially the jump to default.
Yeah.
Okay.
And let's say, and now we have to describe this hybrid model.
It's essentially like a jump diffuser,
Okay.
effectively. right? Because you have, you can think of the default as a jump to 0 or jump to the barrier, and the Merton is, yeah, you can think of the default, you can think of these reduced form model as a jump to 0 of the assets, and the Merton is whether or not you're below 0, below the barrier at time cap t.
Yeah,
So you
yeah.
basically have this diffusion with a jump process.
right.
So it's like
Like
a jump
say-
diffusion.
I mean, early on in your talk, you had several distinctions between structural and reduced form.
Mm-hmm.
And one of those several distinctions was whether tau, the default time, is sort of directly specified versus like derived. So it's like I
Right.
think it's exogenous versus endogenous.
Right, structural versus reduced, right? The difference.
Yeah, I'm trying to avoid that language, let's say. Okay. So here, I would say tau is not completely endogenous like it is in Merton,
Mhm.
because of the reduced form component.
Alright.
Yeah. But let's say, you could say that you're basically doing exogenous specification of tau, and the Merton part is just, how Merton ends up evolving or figuring out the distribution of tau in his model. Yeah, okay, so I just want to make that point.
Okay,
Yeah.
Harvey, a quick question, please.
sure.
So if, in the Bern model, it's just a single day when you know there's a default amount,
Mhm.
which is the final maturity of this compound.
Right.
So I'm not clear what the continuous stopping time means in this case.
Well, it's a continuous process being below a barrier.
So if lambda is like the
Right.
implied probability.
Think of the
from-
barrier. Okay, so you can think of the for Merton, you can think of the barrier, right? You have a geometric Brownian motion. You can think of the barrier as being 0 up to time cap t, and then it becomes at some level at cap t, and then it stops. Okay. But you could do the same thing here with the Black Cox model, where you have a non-zero barrier through time. You do exactly the same thing and combine the models up. The point being that you could just work directly with the survival curves or the hazard rates and combine the models in an appropriate fashion and get kind of mix the properties
Yeah,
together.
mixing is exactly the right word. Like to a probabilist, when you mix, you actually start with two probability distributions for tau, using a convex combination of them. And I think that's what you're doing.
Okay, so now in some of in the literature with the information, they basically define what I call a forgetful Merton model. Right? This is where you have it's Merton, same exact structure as Merton, except that you know the firm value v at time 0 and you don't know it in the future. So you're basically taking the filtration out. So we can just write that down directly again in terms of survival curves. Now the survival curve is even simpler because the probability of defaulting, as far as you're concerned, is based on the original value of the process. You don't have any more information. You know it's going to occur at time cap t, and you know it occurs with a certain probability based on your information from time 0, and that's all you know.
So this forgetful Merton, I understand that you don't know v of t for little t of future time.
Right.
Does that mean you know the probability distribution of v at little t, or you don't even know that?
No. Well, you could know the distribution.
You do know the probability distribution?
Well, you know the process, right? Right, you know this process, say. You know the mu, you know the sigma. You know it started at v0.
So like what's the distinction between Merton and forgetful Merton?
In Merton at time little t, you know v sub little t. And forgetful
Okay, yeah.
Merton, you don't.
Right, and okay.
So you don't know what the
Okay, so
evolution,
that
you don't know,
partially.
you don't know what the Brownian motion has done since then.
Since then,
Since time 0.
since time 0. Okay, that's
Yeah.
fine. So, but when you're in forgetful Merton, when you're at little t and you don't know v of little t because you don't know what the Brownian motion has done between 0 and little t,
Right.
do you at least know something about the probability distribution of this v at little t that you don't know?
Well, you know it's, you still know mu and sigma.
You still know mu and sigma. Okay. Okay. Thanks. Okay.
Okay, but what ultimately happens is the model becomes like flipping a biased coin in time t, cap t. which you can see immediately from this.
Okay.
Because you have a probability of being below the barrier, and you don't know where you've gotten to, so you can't update that information until cap t when it happens or not. So for you at this point, you can so it's very simple to express this in terms of survival curves, and it's very easy to see that it's a biased coin flip, and and just as easily to see that it's accessible and not predictable. What's interesting is that you take this limit that we've been looking at, the limit as you approach this default time cap t of the survival probability, and it goes to 1 minus p. It doesn't go to 0, it doesn't go to 1, it goes to 1 minus p.
Okay, yeah. So, let's say these people involved who forget Holmberg, they, let's say, randomize v of little t compared to what Merton did. And let's say alternative would have been to randomize the barrier instead.
You can do that as well.
Yeah, exactly. So, like, is there any reason to prefer
do
one
one?
to the other? Yeah.
If you're playing with filtrations,
Okay.
if you're trying to keep the same setting but take information out of the filtration, you have to do it this way.
Okay.
Right? Otherwise, you're doing something a little bit different. You're saying the barrier is a random variable,
Yeah.
which would be equivalent mathematically. You would get the
Right.
same formula.
Right. Okay. Okay.
But this shows that they're mathematically equivalent also.
Okay.
Okay, so similarly, you can do it with black cocks. You get a more complicated formulas because the probability of hitting a continuous barrier is a little more complicated, but you just write down it comes from barrier options. It's easier enough to write it down. And now in the black cocks version, it's a predictable model, and you see that the limit of the survival probability goes to the indicator. Again, if you're defaulting at time cap t, it goes to 0. If you're not defaulting at time u, it goes to 0. If you're defaulting at time, you're not defaulting at time u, it goes to 1. Okay, and then similarly, you can add a coin flip to the black cocks. Let's say it's black cocks, but when you hit the barrier, there's a chance of defaulting, a chance of not defaulting. You don't know what it is. Now the model becomes accessible but not predictable. Let's say it's a 50-50 coin. So now the limit becomes a half instead of 0 or 1 as you approach the barrier. So on to now motivated by those examples, we'll make some conjectures. Okay? First conjecture is that the following are equivalent. Tau is predictable, means that essentially the limit as you approach any given time in the future is the indicator of defaulting at that time. Okay, so the idea being, if tau is predictable, then as you approach a default, the probability of defaulting should go to 1. And as you're not approaching a non-default, the time that you don't default, the probability should go to 0. Anything else happens, then it can't really be predictable. Only problem is we can't exactly take these limits. In all the examples that we did, we could take the limits because we had explicit expressions for the survival curves. Not up to measure 0, just complete. Right? So the measure 0-ness is going to mess this up a little bit. So one direction we could prove easily enough, right? If the limit of the survival curve is the indicator, then it's immediately predictable. Because you just predict it by announcing how close the survival probability has gotten to 0. Okay, and formally you just can write it down like this. Okay? Right, at time u, you're 1, but 1 over n later, you're less than 1 over n. Right, so you've survived up to time u, but u plus 1 over n, you're very close to defaulting. Okay, take those times and make that tau sub n, and it goes to 0. It goes to your default time. Okay, now predictability implies continuity, we can almost surely prove. Okay, so for example, consider the set tau greater than cap t. You can write it, and if it's predictable, we have this tau sub n converging to cap t. So we can write it as the union of the states in which tau sub n is greater than cap t. We can also write it as the union of the states where tau sub n is greater than or equal to cap t. Doesn't matter. Now, for any stopping time nu, the set of states for which it's greater than or equal to cap t is the intersection of the set of states where it's greater than or equal to cap t minus 1 over k. Okay, because these sets are nested. If you're stopping at cap t or later, you have to be, well, look at it the other way around, right? If you stop before cap t, then you have to have stopped at some time that's less than cap t minus 1 over k for some k. So it falls out. Okay, so only the times where you haven't stopped yet are in the intersection of all of these. So anyway, tau is greater than cap t is equal to the union of these tau sub n greater than 1 over t, which is the union of the intersection of the tau sub n greater than t minus 1 over k. And since we've expressed it as a union of intersection of sets that occur at earlier times, we get the limit of the conditional expectation is the indicator function. Okay? Unfortunately, this equality is almost everywhere. It's not equal, it's equal up to a set of measures 0. Because of the conditional expectation is only pinned down up to sets of measures 0. The problem being that usually the probability that tau is equal to t is measure 0. So you need, now despite all the examples working correctly, if you try to go down and prove it and you haven't picked the right version of the conditional expectation, it doesn't work.
Yeah. So I guess you say you prove that predictability implies continuity almost surely. Is that
Something along those lines.
Yeah. Okay.
Now, similarly, what we would conjecture is that if we fix the definition of the survival probability, then being totally inaccessible would mean that the survival probability always goes to 1 if you haven't defaulted before cap t. Now notice the difference between these is whether it's 1 or 0 at tau equals t, which is usually a measure 0 set, and that's what's causing the whole trouble. Now we can also almost prove this, right? Take x sub t to be the indicator of tau greater than or equal to t, and take a to be the compensator of 1 minus x, because usually you write the compensators in terms of the other direction. S stability of cap t is the expected value of x sub cap t. A is an increasing continuous process. Right, 1 minus x minus a is a martingale, so it's equal to the conditional expected value of the future values. Just work through the expected value. Over here you have the expected value of x sub t. The 1's cancel out. And the difference here is you have the x plus at, and you have the survival probability plus the expected value of at. So the limit of the survival probability is the limit of the x plus the a minus the limit of the expected value of a at the future time. So what you kind of need is, well, the x, you know what the limit is. It's going to be the indicator, because x sub t is just equal to this process. And the limit is, and you know what the limit of a is, because it's a compensator. You know that the limit of kind of the expected value of a is equal to a. So that basically seals the proof, but only again up to measure 0. Right, you'd have to kind of you have to nail down A here as well as nail down the conditional expectation of X. Okay. But if the above conjectures hold, then we would expect that tau is accessible if and only if the probability goes to something between 0 and 1 on t equals to cap t. Tau equals cap t. Okay. Now, here is an example of how this goes wrong with the measure 0 sets. Right, think of a random variable y. Think of a process x of a little t to be the conditional expectation. We think of x as a process, but as I mentioned, we have different measure zeros at different times. Even if we take two RCL versions of this, we have the two processes are equal on almost all paths. Right? They have almost all paths are the same. But we still have, for s of t of u, as a function of u, we have different measure 0 sets at every time u. This doesn't matter for HJM because we're usually concerned with pricing, in which case all we're doing is expected values. But for what we're trying to do of getting the survival curves to tell us about the predictability, we need the right version. Okay? So this is one way in certain cases of maybe pinning it down. If I could prove this all works, right? We can think of tau always being given by a process, hitting a barrier, hitting 0 even. Okay? It's easy enough. Let y be the min of x up to time t. Okay? Then, I should have done a slash tau. The indicator of tau greater than t is the indicator of y being greater than 0. Now let's say x is Markovian. Then the expected value of the indicator y given ft is the same as the expected value given the value of x and y. So the PDF of y given ft is a function of xt and yt. So we write down the function. Okay. So now write down s in terms of values of x and y directly in terms of an integral of this function f. Now we've defined s not up to measure 0 sets, we've defined it completely. So if any, you would think that if any version of s works for for these conjectures, it would have to be at least this one in the case where it's given by Markovian processing a barrier. But I haven't proved it, so it remains a conjecture that this works. This does it. But I mean, this is kind of formalized. This is pretty much just formalizing all the examples that we looked at. Right? So, in all the examples that we looked at, it works. And they're all essentially can be expressed as Markovian processes hitting a barrier and just being very explicit about the PDF. It's basically kind of taking the physics point of view of stochastic processes instead of the mathematical point of view. Okay, a little bit more. Right, in interest rate modeling, you usually talk about the spot rate minus log of the zero coupon bond price divided by the remaining time. And the spot rate, or the instantaneous, the short rate is the limit of the spot rate as time goes to 0. We can do the same for default modeling. Take the limit of the survival probability, call that kind of the spot hazard rate. Take the limit as time goes to, cap t goes to little t of the spot hazard rate to find out to be h sub little t.
Yeah, that's what I was saying up there in the top right corner. When you started, that, you know, if you solve that equation for lambda, you'll get this equation 1.
This is a different lambda.
Because it's a term, lambda, is that way?
Yeah,
Yeah.
it's basically, this lambda is kind of like the integral of this lambda.
Yes, okay. That's true. All right.
Okay, this is like the instantaneous forward rate curve,
Mm-hmm.
and this is the spot rate curve.
Yeah, okay.
So now what do we have? Well, we have R exists for any time greater than little t.
Mhm.
The only problem being with it is that the limit might not exist, right? You can think of examples where you have really nasty cumulative density functions like double staircase, so that the limit wouldn't exist,
Yeah.
which kind of messes things up a little bit.
Only mathematicians would think that. But okay, but.
Barring, yeah, if we take out the part that's not absolutely continuous,
Yeah. Okay.
then it works.
All right.
Right, and H only exists if ST, little t of cap t is differentiable at the time when cap t equals little t. So now we have further kind of correspondence between HGM and credit, right? The corresponding equations between lambda bar and S corresponding to the rate and the zero coupon bond price. We also have in HJM, or in interest rate modeling in general, that the zero coupon bond price is the expected value of the integral of the short rate. On the credit side, what we expect to happen is that it's equal to the integral of the instantaneous hazard rate if it's totally inaccessible. And H should be 0 if tau is predictable. So reconstructing the survival curves from the instantaneous hazard rate breaks down in a way that doesn't break down in the interest rate case. And of course, because lambda sub little t of cap t is distribution derivative, this H might not exist, whereas in interest rate modeling, it essentially always exists.
Okay. We're going to need to wrap up.
Okay, well, I've got basically 3 more slides. Okay. So, right, ultimately we expect, if all those above conjectures hold, then you're going to see that tau is predictable means that the survival curve goes to the indicator, and the corresponding integrated hazard rate. What did I call that thing? The spot hazard rate, right? The limit of the spot hazard rate should be infinite because you're going towards a default as you approach a default, right? Right, essentially the survival probability has to go to 0, which means that the spot hazard rate has to go to infinity. Okay, and similarly, we expect that if it's predictable, the instantaneous hazard rate has to be 0, which is proved under certain conditions in these papers, but kind of a very restricted, certain restricted conditions, not in general. We also expect that if it's totally inaccessible, if you can just express it as the expected value of the integral of the instantaneous hazard rate. And that's basically it. This is, I guess I should put this at the beginning because this is more like, gives you an example of what hazard rate curves look like. Right, you've got a hazard rate curve as you get to the future. Maybe it gets steeper because you're approaching a default. If you're predictable, you'll notice the slope. If you're predictable, I guess the slope should be 0 at time 0 at the current time. This might be an accessible stopping time because you have this jump, or it could be predictable like in Merton. We mentioned we can put together models. This is a bit more along those. We already went through that in the examples, right? Where you can take the minute 2 hazard rates by multiplying the survival curves if the 2 processes the 2 stopping times are independent. Similarly, you can take the max of the 2 and then you're multiplying the CDFs instead of the survival curves. So the math is all pretty simple. And then finally, we try to decompose everything, right? We take a survival curve, we can try to strip off the accessible part by computing the conditional expectation of the instantaneous hazard rate. So you have a stopping time, you have the survival curves, you construct the instantaneous hazard rate, create a new survival process by doing e to the minus integral of the instantaneous hazard rate. And that should be the totally inaccessible component of your stopping time. Predictable component should be the times where the limits work properly. And then everything that's left should be accessible pieces. And ultimately what you're hoping to see is that you've constructed 3 stopping times which partition the space into the accessible, the predictable, and the totally inaccessible, and your stopping time is actually the minimum 3. And that's basically it.
Good. Great.
Okay, thanks.
Any questions for the speaker? Do you have one? All right. Okay, well, thank you very much. Really appreciate it. Okay. So,